So, next let's look at pruning open. So, in general, if you are talking about search spaces, then it is open which tends to grow faster. So, we saw this, for example, if we have 4 children, then we have 4 successors at this level, then we will have 16 at this level, and then 16 into 4, which is 64 at the next level, and so on essentially. It's the open list which tends to go in general faster, and we saw that that's why DFID, when we first looked at DFID, we said that it doesn't do too much extra work. We said that it does B divided by B minus 1 times, because the number of nodes, the internal nodes in an exponentially growing tree is typically much smaller than the leaf nodes at any level essentially. So, pruning option open is also something that we are interested in. And the simplest way to prune open is to use a beam search, some with beam width W. We looked at beam search as a variation of hill climbing when we were optimizing the H value. The only difference was that hill climbing, we said that choose the B best successors, but only if they were better, because we were trying to optimize the value of the hill climbing. And the termination criteria at that point was that there are no better successors and you could get stuck in local optima. But in the context of finding a path to the goal node, which is what we are interested in, we are really optimizing on the G values of the goal node essentially. We want to find the shortest path to the goal node essentially, and nodes chosen based on F values essentially. So, if you remember the recursive best first search algorithm, for example, it always picks nodes based on F values, but the problem with F values is that they are known to increase with depth. We saw this in the example also, and we saw that especially when the monotone condition is satisfied, it becomes a property of the graph. So, you can't choose this only if better criterion, which was there in the earlier hill climbing and beam search algorithms. We will say that even if not better, then you always keep the W best successes, where W is the beam width, and that's a variation of beam search that we will look at essentially. The termination criteria is going to be goal found. So, we hope that the heuristic function will be reasonably good, so that even in an infinite graph it will be found. For a finite graph anyway, it will find a path to the goal. It may not necessarily be the optimal path, because the heuristic function may not be the best, but it will find a path to the goal node. The total space required by beam search will be width into depth, because at every level we are storing W nodes and we are going up to some depth D essentially. So, it is a linear space algorithm, but it is not necessarily optimal, and we have already saw a figure of beam search. The same figure applies here essentially. So, the total nodes that you are going to be keeping is W at every level, and because the depth is D, so W times D essentially. But we are going to be searching on F values, and we have already observed that F values tend to increase with depth essentially. So, our termination criteria is going to be again that the goal has been reached essentially. If you wanted to find an upper bound cost to the solution, the lower bound cost is h of s, because h is an underestimating function, and we know that it will be at least that much. But we are interested in upper bound, because sometimes we want to do some pruning based on that. We could find some path starting from the goal using beam search and use that cost as an upper bound cost. So, we just spoke about the beam search. So, what is the beam search algorithm? The beam search algorithm maintains a beam of width W. In this diagram, the width is 2, but in general it can be larger, because nowadays memory is cheaper. And we always choose the nodes with the best F values at each level essentially, and we keep doing that till we reach the goal. So, we assume that it will find a path to the goal. We can't use the older criteria of move only to better nodes, because we know that F values increase as we go towards the goal, and now we are working with F values, not with H values as we were doing earlier. So, very often we will see that if we can estimate an upper bound to the cost of a solution to the goal, then that upper bound can be used profitably to prune the search space further essentially. And we can find an upper bound on the cost by just using beam search, and so some path it will give us. So, we know that we at least have a path of the cost given to us by the beam search. So, that will become an upper bound. We do not have to go for a longer path. So, let the cost of the path be u, then this can be used as an upper bound for other search algorithms. So, it is a upper bound on the cost of the optimal path, because we have a cost of path of cost u. So, the optimal will only be better than that essentially. So, basically what we are saying is that we need not look at nodes whose f values are greater than u. This u is an upper bound cost that we have found using beam search. So, if this is a start node and this is a goal node, then this u gives us a kind of a boundary which says that you need to search only within this range essentially. Do not look outside this range. If a value f value of a node becomes greater than u, then you do not have to explore it any further, because we know that f values keep increasing, and any path going through a node, for example here, will, if f of n is greater than u here, any path that goes through here will be longer than this upper bound value. So, we do not need to explore that. So, such nodes we will not explore. So, the search frontier for A star is always going to be within that. We have already made this observation that for any node that A star picks, its f of n is always less than or equal to f star of S. So, which is always going to be, which is less than the optimal cost in any way. This optimal cost we may not know, but it is going to be less than that. So, it is definitely going to be less than or equal to the upper bound essentially. So, for A star this property already holds essentially, but we can think of other algorithms where we can exploit this fact essentially. So, one of the algorithms that we look at is called breadth first heuristic search. It was also given to us by Zhao and Hansen in 2004. So, there was a spurt in A star and variations around that time, and quite a few algorithms were proposed. So, if this is your start node and this is the goal node, and if you had done breadth first search, then breadth first, so our algorithm is going to be breadth first essentially, which is what, go level by level deeper into the search space. Breadth first search was blind, and its open is not influenced by the goal at all essentially. What if we use breadth first search and use this upper bound to limit which nodes in the breadth first open we will search essentially. So, limit breadth first search to f values less than u. So, we had said that u is like a plot of f values, which is all those nodes whose f value is less than this u. What is u? U is some path we have found to the goal. So, we know that we can only look for a better path. We do not need a path worse than that. So, any node which is outside this boundary, we do not have to search essentially. So, this breadth first search, breadth first heuristic search, the name sounds like a contradiction in terms, but it is actually a blind search, but it works within the boundary u. That is why we call it heuristic in some sense. And the search space, the search frontier for BFHS or breadth first heuristic search is only a small part of the search frontier that breadth first search would have had. Remember that breadth first search had no sense of direction, it would go off in any direction, and that is what Branch and Brown also did. But now we are saying, okay, you do blind search, but stay within this boundary which is given to us by this upper bound u, which we have calculated by finding some paths to the goal node. Now, this will also find us an optimal path essentially. And it has been empirically observed that the search frontier of breadth first heuristic search is smaller than the search frontier of A star algorithm, and this is an empirical observation. Beam search, we have already spoken about it. What does beam search do? That instead of maintaining this open of breadth first heuristic search, beam search only looks at a fixed number of nodes at every level essentially. So, this diagram shows in this green curve the open list for breadth first heuristic search, and inside that, which is in this region here, is the closed list that breadth first heuristic search would have maintained essentially. Beam search by definition has a constant beam width, this thing. So, it will only look at some subset of the nodes that breadth first heuristic search will do that, and we have already observed that beam search is not admissible. In fact, the solution found by the beam search algorithm we are using as the upper bound, which means that we know that it is not necessarily the optimal, that we could find better solutions. But this is how beam search would look like. It is open and closed, we have already mentioned. It is if this is W and if this is D, then the total number of nodes kept by beam search is W into D, which is linear in nature. And remember that our focus is on saving space at this moment. Of course, with the warning that beam search is inadmissible, but it's got linear space. That's a plus point. Now we can use this idea of divide and conquer here as well, and Zhao and Hansen did that. So they have this algorithm called divide and conquer breadth first heuristic search, which is, remember that this is the boundary U within which the breadth first search is, and it maintains, in their style of smart memory graph search, it maintains a list of open nodes and a list of boundary nodes. The open nodes are in green or cyan and the boundary nodes are in yellow. But because we need to reconstruct the path, it also maintains one or more relay layers essentially. So, that is divide and conquer breadth first heuristic search essentially. We can extend this idea to divide and conquer beam search, and it keeps only 3 layers of constant width. What are the 3 layers? One layer is open, the other layer is boundary, and assuming that there is only one relay layer, the third layer is relay, but in principle you could have more than one relay layers. So, we are talking about divide and conquer beam search. So, it is beam search. So, it started off with linear search, but now we are saying of those all those D levels, keep only 3 levels, one for the open, one for the boundary and one for the closed. So, which is why they have constant width essentially. So, which means divide and conquer beam search has constant space requirements. It will keep B, not B, yeah, if B is the beam width, then it will keep B into 3 layers essentially, or if W is the beam width, it will keep W into 3 layers essentially. It is a constant space algorithm. The only thing is, as we have said as a warning, that it is not admissible. It will not give you the optimal solution necessarily. It could, but it may not essentially. So, beam search is inadmissible, which means divide and conquer beam search is also inadmissible, and we terminate with a non-optimal path. So, the next algorithm, which is also given to us by Zhao and Hansen. Hansen was a supervisor and Zhao was a PhD student working on this problem. Is called beam stack search. It is a very interesting idea. So, let us look at that. Beam stack search is like beam search plus backtracking. So, a little bit like what we did with recursive best first recursive best first search. Essentially, you followed the heuristic function, but you can backtrack essentially. Except that in recursive best first search, we kept only one best successor. In beam search, we keep many essentially. So, backtracking is explicit and it is guided by something called the beam stack, because remember that we are not storing everything, and they introduce a data structure called the beam stack, which is as follows, that at every level it kept two values, two numbers. One is f min, which is the value of the node with the lowest f value in that beam. So, remember that a beam has some number of nodes, whatever the width is. So, this is f min. Let us say that these nodes are ordered in increasing h values, and so one is the lowest f value is the f min, and the highest f value which is not in the beam is f max, which is why we have an open interval here and a closed interval on the left hand side. So, what does the beam stack contain? It contains two numbers. One says that in the beam at that level, so these pairs of numbers are stored at every level in the beam stack, and it says that at that level the cheapest node in the beam has a value of f min, and the cheapest node which is outside the beam, which is higher than f min, has a value of f max essentially. And these two numbers, so it is a list of numbers that it stores, and it uses them to guide the beam stack search when it is backtracking. The pair of values in the beam stack, they store the identity of the current nodes in the beam essentially, used to guide the regeneration of nodes when you are doing backtracking. So, beam stack search orders nodes on f values, and it slides this f min f max window when it backtracks, but it always stays within this upper bound of u essentially. So, this is how it looks. Let us say the beam width is 3. So, at every level you are storing 3 nodes. So, we have seen 2 levels here, level k and level k plus 1, and the leftmost node, and these are assumed to be sorted with increasing values, f values here. The leftmost node is the cheapest node, and just outside that is f max, which is not in the beam width. So, when it backtracks, it knows where to start the next level from. So, if you want to backtrack from level k plus 1, you go back to the level k and then generate all the nodes which will be starting from here essentially, and that is what is happening, is that you know at next level which are the nodes which will go into the beam width. So, using this as a guide, this beam stack search can search the entire state space. So, if you assume that the f values are sorted from left to right here, then beam stack search essentially maintains this beam width, as you can see in the nodes on blue, which sweeps from left to right searching the space, and these red nodes are the upper bound beyond which it need not search, because we know that that we already have a solution of that cost. So, the last thing that Zhao and Hansen presented was called divide and conquer beam stack search. So, if you remember divide and conquer beam search, it is a similar this thing. It maintains 3 layers of constant width nodes, except that it will now backtrack and search this entire space which is within this red boundary, which is defined by the upper bound u essentially. How does it do that? That is a interesting part. Divide and conquer beam stack search has deleted the parent nodes because it is maintaining only those 3 layers. So, how does it work? It answer to that is that it regenerates a node from the start node. That is the important thing. Every time it needs to backtrack, instead of going to the parent and then coming down to the next node, because the parents have been deleted except for those 3 layers, it regenerates from the start node, and at each level it is guided by the values in the beam stack. So, it knows that where to look at the next level essentially. So, in that sense, The space complexity of divide and conquer beam stack is of the order of 1, which is the space complexity of divide and conquer beam search, which is same as beam stack search essentially, because it maintains 3 layers of constant width W. So, those 3 layers that we spoke about, the relay layer, the boundary layer and the open layer. But here we are ignoring the memory needed for the beam stack, because beam stack is of depth D, and at each point it stores 2 numbers essentially. So, if we ignore that part, then it is of constant time, constant space algorithm. So, we started with A star, which required exponential space, then we saw how to prune the closed, then we saw how to prune the open with beam stack search, and then we are saying with divide and conquer beam stack search we are going to work with a constant space algorithms. So, with that we end our study of A star